named for a car. It's actually named after the Pleiades, which is Subaru in Japanese. Actually, the original Subaru name was pronounced Sumaru. So Sumaru, Sumaru. But it means, quote, to get together, unquote, or to tie together. And that's a fitting name for the Subaru telescope because it binds our knowledge together and helps answer lots and lots of questions. The Subaru telescope is an amazing telescope. It's 8.2 meters in diameter. Now that's 26, almost 27 feet in diameter. That's huge. That's huge considering that the Hale telescope in Mount Palomar at 200 inches used to be considered huge. Well, this is now 26.9 feet in diameter. All right. And that is just astonishing. And it has a new technology basis for it. It's one massive mirror, though. It's not multiple mirrors like the Keck telescope. It's actually one singular mirror, but it's being driven extremely with extremely fine electronics to actually make it the most accurate of all telescopes that we have on the planet. So that's pretty cool. And so the Subaru telescope, by doing this deep imagery of Saturn's environs, it found these moons. And the moons, tend to orbit around the planet in one particular direction. If we pick a direction and look down, say, on top of the solar system from what we define as the top, then we say all the moons move counterclockwise around a planet, or so forth, or planets around the sun counterclockwise. Well, in this particular case, we found that this isn't exactly the case for these new moons. And it's not the only place. So what do I mean by that? Well, this direction I'm talking about, this standard direction, this counterclockwise, quote unquote, as we call it, it's based on the original formation angular velocities of the original cloud from which everything formed. Okay, the Earth happens to be spinning in that counterclockwise fashion. The major cloud around the sun was spinning in that direction. So this is why things rotate the way they do. Now, because of that, some of the moons we find are all rotating in this manner that makes a lot of sense to us. But then we see things that don't make sense. And now it seems some of these 20 moons that we've found with the Subaru telescope are violating this directional law, and they're actually going in the opposite direction. All right. Now, this is pretty weird. Now, there's other bodies in our solar system that violate this. Venus is a big one. The entire planet Venus spins in the opposite direction than the other planets. Okay, I have to say most other planets because there is one that's a real oddball, and that's the next one. Okay, now Venus spins in the opposite direction, and that could be a consequence of an early impact with something when it was first forming. In simulations that I've done, I've actually shown that a planet in its early formative stages, if it collides with a big enough object, it can literally change its rotational direction very, very fast and start going in the opposite direction. And that could be what happened to Venus. We don't know. But I say most other planets because Uranus is flipped almost 90 degrees on its side. And that's a weird planet. So it's like it's rolling through its orbit like a bowling ball rather than spinning like a top, which is really kind of weird. And some of the moons of the planets in our solar system have orbits that are opposite that of other moons. Okay, now when I say opposite, what does that mean? If they move in this normal, quote-unquote, counterclockwise fashion that we're so used to talking about, we call that prograde, Prograde, prograde. If they move in the opposite direction, we call that retrograde. Okay, like retro rocket grade, so retrograde. So some of the moons in our solar system are indeed in retrograde orbits, going the opposite direction of the other moons in that very same system. And that's what we see in Saturn's case with some of these moons. And it's an odd finding because you say, well, how can that happen? Now what are some of the reasons why moons can be going in the opposite direction? All right. I don't know that many people think about that, but in nearly all the cases, it means that some type of catastrophe settled out into a rhythm that we see to this day. And what might have been that catastrophe? The first thing to think of is collisions with something else. Second thing to think of is an asteroid coming into, say, Saturn's nearby environment and getting snagged by Saturn and settling into an orbit that ended up taking it in a retrograde or opposite direction of normal direction. And that's something that could have happened. So I think it's interesting when we look at these new findings, especially Saturn's new moons, that we have these moons that have been found that are actually going in a retrograde direction. Just so strange, you know? Now, for instance, if we look at other moons in our solar system, most of the moons that are like an asteroid size, okay, are going in a prograde direction, you know, the normal direction that we expect. All right, that's the same direction in rotation as the parent body, the parent planet. All right, most of Neptune's moons, for instance, are prograde, except for Triton. Neptune's largest moon is retrograde. So imagine moons that are going in a prograde direction, and then Triton going the opposite way, the biggest moon of all, going the opposite way around you. I mean, that's a dizzying prospect to me. I don't know. So, you know, now, and most of the asteroids in the asteroid belt have prograde or normal orbits, but there are a few dozen that have retrograde orbits. Now, what could have caused that? Why would they be why retrograde? Why would some go in one direction and some go completely in a different direction? Could they be captured interstellar objects? That's a question we can't answer. It might be. Remember, the universe has been here for, you know, well, our universe, our local universe has been here for 4.6 billion years, okay? And that's the universe created by the sun and its solar system, its retinue of planets, all right? However, so it could be these interstellar objects that got caught and ended up being, you know, migrated to the asteroid belt, perhaps. Who knows? Or it could be the result of a collision. Maybe two asteroids struck and enough momentum was imparted to one of the pieces of debris that came off that it was going in the opposite direction that everybody was moving. And it could have settled into an orbit that way. But the chances of something like that happening are actually quite slim, if you think about that, because if you have a collision, you're going to be slowing something down drastically, which means that it's not going to have enough energy to stay where it is. It's going to end up having to be farther away to be stable, okay, because things move slower in their orbits the farther away they are from the sun. But if the stuff moving toward the sun is moving a little slower, it's going to end up in a orbit that's closer to the sun. Maybe that's the origination of the near-Earth asteroids. Maybe the NEOs, these near-Earth objects that we see, are the result of billions of years of collisions and objects that got captured in more nearby orbits, local orbits in the inner solar system. It's fascinating. I mean, our solar system is chock full of debris. I mean, tons, billions of tons, miles and miles of asteroids, you know, in diameters, if you want to add them all up. And so we actually are in a very volatile place, you know. And the other thing that they could be, these retrograde asteroids, they could also be comets that are no longer viable. And a comet is made up of rock and it's made up of ices, right? Actually, quite a lot of different kinds of ices other than water ice. We've talked about this a couple times in the past. And these could have been just the rocky cores left behind of comets that are no longer volatile and outgas all this stuff as they get closer to the sun. And they could have had interactions with Jupiter over the years, which ended up causing them to have these retrograde orbits out in the asteroid belt. It's entirely possible, you know. And I think that, you know, when we look at our solar system, I think it's a good time to mention that we have a moon, and a lot of people will say that our moon is really an oddball size. But you know what? I'll be honest, we don't have anything to compare it to. We only have our own solar system, right? We have Mercury, we have Venus, and we have Earth, and we have Mars. Well, Mars has two asteroidal moons, which are probably captured, Phobos and Deimos, okay? And Mercury has none, Earth has one, Venus has none. So the question is, does our solar system and our planet Earth, with its fairly large moon, Does that represent normalcy for solar systems to have planets with somewhat large moons? We don't know because we haven't been able to find moons yet. We have hints. We actually have some glorious hints of moons, exomoons as they're called, in other star systems. But we don't have any solid data that shows any kind of trend or any kind of pattern. Frankly, I think there is no pattern. I think that it's very likely that the stars will always have surprises for us, and that's, I think, very true. Now, I wanted to throw it out to both Daryl and Amanda to see whether they have anything that they want to add regarding the moons.
I was sitting here thinking our prograde objects, those orbiting in that conventional counterclockwise direction as seen from the north, are they more likely to be in the equatorial plane of the planet they're orbiting, or then again in the, near the ecliptic plane of the solar system? I suspect, and I think I've heard, that a lot of the ones that rotate in the opposite direction are captured objects, and a lot of them, I think, are not in the orbital plane of the solar system. Pluto, as an example. Pluto, I think, is 17 degrees off the plane or something like that.
It is indeed, yeah. Right, yeah. And that's an excellent observation by our man Daryl, our other astronomer on the ground here. And that's very true. And so the question becomes, are these retrograde objects that have like highly elliptical orbits, really odd elevations? Some yes, but some no. Like, for instance, the 20 moons found out by Saturn, these are all tiny moons, a little bigger than asteroids, a little smaller actually than asteroids of various sizes. And they're actually in the ring plane of Saturn. So that's pretty interesting that they are still in the ring plane. So I don't know, but those are retrograde. So how could that have happened? And honestly, we don't know. Isn't that wonderful? I mean, not knowing is the reason that we do this at all.
They're in the ring plane, but they're going retrograde?
Well, ring plane, it doesn't mean that they're in the rings.
I understand that, yeah, but I mean, they are, you could say by definition, if they're in the ring plane, I guess they're orbiting equatorially around Saturn.
That's correct.
But yet they're still retrograde.
Yeah, which is an oddball finding, and so I think that whereas we do have objects that are retrograde, like captured comets and things like that, that will have these elliptical orbits that are actually elevated to the plane of the solar system, some are not. There's a dozen asteroids that orbit retrograde. Several, actually, I think just over a dozen, that are retrograde objects, and we don't really know why they're retrograde versus prograde. I don't want to be on the wrong side of the highway traveling into oncoming traffic, but that's what these guys are doing. Now that promotes collisions over time, and I don't want to be part of a collision with an asteroid at some a million years in the future when the results of a collision a million years ago was the destruction of the Earth. But who knows? Who knows? I mean, maybe, and then this is another thing that I have been postulating for a number of years now. Maybe the existence of the moon around our planet is not as conducive to the formation of life here as we might have originally thought. I look at the moon as another gravity well, a source of gravity that attracts objects to the moon-Earth system. All right? And if that's the case, then looking at the moon and looking at all the craters and all the impact events that have happened on the moon, to this day they still happen, then I think that perhaps the moon has hurt us more than helped us. And then people will immediately say, rightfully, but wait, the moon is responsible for our tides. And the moon causes the tides that dry out certain areas for several hours at a time, giving life the chance to move out of the oceans. I mean, that's what it was all about. The moon is the reason why the Earth has slowed down over time. It used to be a 4-hour day here, Well, that'd be great for work. Hey, I just got to work and got to go home. All right, hey, I'm out of here. Have a fun weekend coming up in just a few hours. Well, the fact of the matter is, if the moon was gone, we wouldn't have tides, is what people say. And the answer is that's wrong. We absolutely would have tides because the sun creates tides. The sun's tides are 40% the size of the moon's. So if we have a moon, then we have this exceptional tide situation here. But as the moon goes around the Earth, those tides change. Okay, we have some higher tides and some lower tides. But if there was no moon, it would be more even based on the rotation of the Earth alone. And had we had no moon in the beginning, I still think intelligent life could have evolved here because the sun would still create tides. And at 40% that of the moon, it means that the tidal flats that are high and dry might be partially dry. Not fully dry, perhaps, but partially dry. In some areas, it would still be fully dry at 40% the strength of the lunar tides. So I think that the possibility that life could have evolved here was great still. However, keep this in mind. We'd probably still have a 4-hour day had the moon not existed. All right, that means we rotate faster, okay? So that would be a very different environment for humans, and we would think of it as not a big deal. It would be nothing to us because we would have evolved into it. It's like the creatures of the deep sea. They evolve into their environment. They don't know any different, but you bring them to the surface, it's like us going into space without a spacesuit. You know, we just, swell up and perish. So, that said, my thoughts about the moon are just those thoughts, but I do think it's pretty interesting. Now, when we come back from the break, we're going to talk about something else that NASA has been, crowing about recently, and it's the Parker Solar Probe. So stay tuned to Sky Tour Radio, and me, Amanda, and Daryl will be back in just a moment.
Oh, did you know I was coming? Here 10 where it's nice and
we landed the Huygens probe on Titan as part of the Cassini mission, and we got that little snapshot of the surface of Titan where the probe landed, and it turned out that the quote-unquote rocks that we were seeing in that camera view were actually the size of pebbles. So it was a very, very close look at the ground. However, the thing that's interesting here is that Titan is sort of like an early Earth. It's just locked in a deep freeze. When could Titan ever become more habitable? Well, in the current state, not ever. However, that's not how the universe is. The universe evolves. Things change. One thing that's going to change is our sun. There's a time when the sun is going to increase in size because it's going to be in its death throes. As it uses up all of its hydrogen, it's going to then swell into a red giant. And when it swells into a red giant, it's going to have a lot higher luminosity. It's called intrinsic brightness. Well, that intrinsic brightness will translate to a lot more energy reaching Titan. And for a period of time, Titan will be habitable. We won't be here because we will either have been swallowed by the red giant that was our sun, or we will have left the Earth and moved into the outer solar system, into habitats that we construct. Maybe we'll become a nomadic civilization where we will have large spacecraft. You know, we look at shows like Star Wars and Battlestar Galactica and Star Trek. That's all about reaching out into the universe, going interstellar. And it assumes we'll be interstellar. Well, you know, art often imitates life, but sometimes life imitates art. The development of the cell phone, right? We have Apple iPhones, and the iPhone is far better than Captain Kirk's communicator. You know, he would say, Scotty, I've got to get one of those. You know, he wouldn't want to stick with his little old-fashioned communicator, right? We've leapfrogged that technology, in terms of the science fiction universe. So clearly, when we're talking about, going out there and getting into the universe and the sun dying, we are going to have to be mobile. We're going to have to get out there. We're going to have to be able to go interstellar. We're going to have to be able to go to the next solar system or to our outer solar system, at least as a stepping stone. Mars might be more habitable at that point. And if it is, then maybe we can set up a temporary location there for humanity and then move on to the stars. Because Earth will be no more. Earth will be a cinder. Everything around you, if you look around, everything you have, the whole world, the beauty of the world, it's going to be gone because the sun is going to destroy it someday. And that's not a supposition of theory. That's fact. And we've watched it happen in other star systems. We've seen planets that actually survived the destruction of their solar system or their star system by the star. They've actually survived, and they're probably very, very different from how they started out. So this can happen, and it will happen here. So we have to get out of here. And Titan is another place that is being looked at as potentially habitable for a period of time. Now, right now, the water is locked up as ice that's hard as granite out there at Titan. Not a whole lot of sunlight gets there, but it's got this nitrogen haze for clouds, a noxious mix that we can't breathe. So we're never going to be able to stand on Titan and just walk around. Currently, it's so cold on Titan that there's lakes of liquid methane and ethane. Okay, this is just unbelievable. Here on Earth, we don't have liquid methane. We have methane ices deep in the ocean where it's trapped and held down by pressure. And those are called clathrates or methane hydrates. And there's these hydrate fields, and sometimes if you change the pressure just a little bit, the methane goes right out and bubbles out and causes some dangerous things. For instance, there was a tsunami one year in Indonesia that as it rolled ashore, it was preceded by a wall of fire. And the giant surge brought this fire on shore, and that fire killed people and burned down things. And meanwhile, then it followed up with water. I mean, talk about a 1-2 punch. Well, that was actually an ignited hydrate field that was loosened by an earthquake. And when the methane got to the surface, somehow it caught fire. And that tsunami generated a wave that, a series of actually surges that brought that methane on shore, which ignited with some of the local stuff going on, and boom, we had a firestorm, water storm. I mean, I would not have wanted to have been there. Oh, what a way to go. So our world has, some strange things now, but just imagine if we go to Titan, where we have more methane now than here. And we're going to be really careful there, So possibly those moons can be habitable. The outer solar system, Uranus, Neptune, I don't think so, not so much, okay? Pluto is got a very tenuous nitrogen atmosphere, so not so much. Jupiter's moon, Europa, it's got a water sea beneath its icy mantle, the icy surface layer, that is, here. And I think that's something that might warm up a little, but it's not going to change substantially out that far. Maybe it will. Saturn's further away, but all these things can change in time, but it's all going to be based on the sun. In the current state, they're sort of in a holding pattern, but humans don't live nearly long enough to see the changes that happen over long periods of time. See what I mean? Amanda?
I'm just thinking, we have no way right now of knowing where, I don't even know if this is possible, this term I'm going to use, where a star might turn on.
Actually, that's a fine phrase. We know that there's clouds, the stellar nurseries, like Orion Nebula, that we view in SkyTour Livestream a lot. In fact, we just did last night. We saw it for a little while. Okay, that's a stellar nursery. What is a stellar nursery? It's a nursery where stars are born. And we've identified, using infrared telescopes, we've identified areas within the Orion Nebula that are infrared hotspots, areas where mutual gravity is coalescing gas, and that perhaps a star will, as you said, turn on. The other term for that is wink on. It's a magic threshold. When the temperature becomes hot enough for hydrogen fusion, where hydrogen couples with another hydrogen atom and forms, in the end, an isotope of helium. Okay, that process is a repeating process that goes on and on and on for the star's life as long as it has hydrogen. And that process is fusion. And this is when the star begins its life. It will suddenly just ignite and go from being a gas cloud to this star in a split second. Now, if you think about that, that's pretty cool. I'd love to see that.
Sure, I'd love to see that too. That would be amazing.
Yeah. And it would just boom.
And there's nothing like that in our solar system.
No, not at the star level. I mean, we don't have this type of hydrogen gas floating around here. Our star was probably born with a few other stars in a cluster. And then over time, as our star orbited the galaxy a few times, we've gone around the galaxy just under 20 times since we were formed. All right. So, for instance, when the dinosaurs were roaming the Earth, our planet was on the other end of the galaxy. Our star was at the other end of the galaxy. So the stars look very different to the dinosaurs, as they did when Lucy was walking around in Africa, or looking up at Orion. There was no Orion per se, and we've used the description that says, well, if Lucy looked at the belt of Orion, she would only have seen like one star, because the other two hadn't been born yet. Well, the truth is, 4 million years ago, when Lucy was around, there might not have been Orion's belt anyway, because of the configuration of the stars. Things move a little bit, so it might have been very different. But still, everything is in motion, you see, in the universe. And so when we look at events in our past history, we kind of have to put that in perspective and say, well, at that time, we weren't even where we are in the galaxy. We were at a totally different place, So there's an awful lot that goes on, but it all focuses around our star, the sun. Our sun is the life giver. The sun is the platform that launched life, in a sense, because of its warmth. It takes things out of a deep freeze. And deep freeze means basically like going into some type of hibernation state. tardigrades or water bears. These little guys can easily withstand 50 years of no water because they go into a state called cryptobiosis, and then add water and just add water and a magnifying glass, and they'll come to life again after many, many years without water. I mean, that is so interesting. That is a hardy life form. And right now, by the way, there's a whole bunch of tardigrades on the moon that crashed to the moon, if you recall. And so actually, you could say there's probably life on the moon, because those tardigrades, as long as they're still in some type of container, there's no reason that they would be quote-unquote dead. You know, they've survived in the vacuum of space. So I think they can probably survive some of the radiation on the moon, especially if they're in a cryptobiotic state. They're not going anywhere. And if you find them someday and add water and pour, you'll probably have tardigrades. You know, I think that's so cool. And actually, going back to the sun, you know, well, first of all, let me say, Amanda, did you have any other questions about the moons or something else? Because you might have had other questions that I might have glossed over. Sorry.
Just the gravity one, but I don't know if it was going anywhere. So I was just wondering if the sun's gravity had any effect on our moon.
Again, an excellent question. The answer is, in short, it does have an effect. It does tug on the moon like it tugs on the Earth. And as the moon goes around the Earth, all right, the sun does tug a little bit more on the moon when it's closer to the sun than when it's on the other side, and not closer to the sun, but it's a small amount. But again, because the universe has nothing but time on its hands, the orbital idiosyncrasies, as I call them, have settled out into a rhythm that lasted billions of years and has continued to go and will continue to go for billions of years. Now, it's true that because the Earth has this ocean, and because the moon is as close as it is, the moon is locked, has one face that's always facing us. That's because of something called tidal locking. And because that's happening, then what's happening is the Earth is actually slowing down over time. As I mentioned, we used to rotate a lot faster. Our day used to be 4 hours long, you know, and by the time it was 12 hours long, we had the oldest rocks that we could identify when Earth's day was like 12 hours long. When it became 18 hours long, that's when the first life forms appeared, the cyanobacteria, when the Earth was 18 hours long days. And so it's after that, and again, as the moon was doing that, as the moon was slowing down our planet, the moon was also basically robbing some of the orbital velocity, and it was actually spiraling away, and it still is. It's moving away from the Earth about 2 centimeters every year. And now the logical question someone might ask is, does that mean that someday the moon will be completely free of the Earth? The answer is, if all things stayed the same, yes. All right, if all things except the Earth-Moon system, then eventually the moon would be free and would suddenly no longer be gravitationally bound to the Earth. The amount of the tides on the Earth from the moon would gradually diminish over time until it was no longer a registerable effect. But that's going to take so long that by the time the moon could actually be in a state where it was free from our gravitational force, the sun will have already swelled into a red giant and destroyed it all anyway. So it's a moot point. But the gravity does affect the moon in the ways that the sun's gravity affects the Earth as well. It tugs on the moon and forces the moon to have its own version of tides, but that's geologic tides, where it's actually pulling on the rock strata, and so it's affecting the tidal bulge of the water for us. It's affecting the geologic bulge for the moon. Okay, so
well, didn't they find ice under the moon's surface?
Yeah, actually, there's a lot of compounds on the moon that actually have ice bound into them. And the L-Cross mission that went to Cabeus Crater on the moon's south pole, the idea was in these areas on the moon, these craters on the moon where light never gets to, because the moon isn't angled in such a way. Remember, it's tidally locked, so the same face always faces us. This means at the south pole of the moon, because the light is at a low angle down there all the time, you can imagine that there might be a crater that is deep enough that the light never gets down into the crater. And that's exactly what they thought. Hey, maybe there's water ice trapped down there. This means if we can find ice down there, this is a great idea, because then we could actually put a moon base on the moon and have plenty of water that we can extract. And the L-Cross mission, in fact, showed that water was present in Cabeus crater and probably in other craters like that. But then other analysis showed that there's actually water in the lunar regolith in a lot of places, not just at the South Pole. So we're no longer confined to having to be near the moon's south pole to have a moon base. We really could set up in Clavius crater, which would be great. For those of you that saw 2001: A Space Odyssey, I think you would agree Clavius is the place to be. So they found water there, and that water is just in the form of ice that is bound into the regolith, into the soils of the moon. So I don't know if you had anything further on that, if you want to elaborate.
No, well, that kind of answered my next question. I was going to say then, why are we close enough to the sun, for life, and yet the moon isn't? Why isn't it getting warm enough to melt the ice? But I forgot about it being tidally locked.
Well, yeah, and don't forget, too, that the moon doesn't have an atmosphere to conduct heat into areas of shadow. On the Earth, the dark side of the Earth is still warm, even though the temperature cools at night. But that's because the atmosphere is warmed, and it radiates that heat back down to the Earth at night.
That's the missing piece. Okay.
Yeah, because the moon doesn't have an atmosphere, so there's no heat that's transferred except through conduction, direct contact with the lunar surface. All right. And when the heat is conducted, say, to the ices that are in the permanently shadowed regions, that heat, it'd have to be it'd be short-lived, because if it's not reaching down into the crater, it's never going to melt the ices, and the lunar regolith isn't conducting enough heat to melt it in the bottom of these craters for the parts that do get lit by the sun. And you don't have to go down too far into the moon's surface, I don't think, to find the icy compounds again. Now, the moon isn't made of ice, don't get me wrong. Mars, however, is. Mars actually has an awful lot of ice on it, both water ice and carbon dioxide ice. The Phoenix lander, I think, when it went to Mars, when it landed, it actually sort of skidded to a halt because it landed on an ice field. And when the thrusters landed, it blew away a lot of the overlying dust, and it landed right on solid ice. So, that was impressive to me. It's like, wow. So this could very well be like a frozen lake on Mars. It never unfroze and may never unfreeze unless we can do your Mars blanket, Amanda, and get it warmed up.
That's what I was thinking.
Yeah.
I was wondering if the Mars blanket would work on the moon.
Well, not without an atmosphere, unfortunately. No. Yeah, there's no atmosphere, and the moon's not big enough to retain one. That's the other thing.
Mm-hmm.
Yeah. So it all comes down to the sun. And when we talk about the sun, as much as we know about the sun, there's so much we don't know. We know what powers the sun. We know it's hydrogen fusion. Our sun is a normal star. It's converting hydrogen into an isotope of helium, and then that process is ongoing. All right. And we didn't know certain things about the sun. We know that there's some convection layers, like a boiling pot near the surface of the sun. We can see this when we look at the surface of the sun. These things called granules. They're dark-edged, irregularly shaped patches on the sun that are very, very small. Well, those are like convection cells in the outer atmosphere of the sun. And they're dark around the edges because that's cooler stuff sinking down around the edges. And the warmer stuff percolating up from the center will look brighter. Sunspots we see in the sun, those are magnetic storms. Think of them as blisters of magnetism at certain areas on the sun. And they're dark. But if you saw them all alone in space without a sun nearby, they would be red hot and glowing. But they don't glow to your eye relative to the brightness of the sun, which is so much and far more brighter. So that's how that works, see? So when we talk about the features of the sun, we're talking about right now the photosphere, the surface as we see it from Earth. There is no quote-unquote surface. It's not like you can go stand on the surface of the sun. If you went toward the sun, you would end up going into the sun until you just burned up. Because as soon as you reach a certain point, it's like going into clouds. They look sharp-edged, as you see them from far away. But as you get closer and closer and closer, the edges are fuzzier and fuzzier. And then the next thing you know, you're in it, and you don't know what's going on. I'm in the cloud, and then you're inside the center of the cloud, and then you're out. Well, you can't go into the center of the sun. The sun's gravity is extremely powerful. The sun's magnetic field is extremely powerful. And the heat is the last thing, of course. That is the main killer for organic life. It's the great sterilizer. It'll end your life very quickly. And NASA launched a probe in 2018 called the Parker Solar Probe. This probe is going to actually make it within 4 million miles of the sun. I think that's pretty good, all right? Considering that that Mercury, the surface of Mercury can melt lead, and Mercury is several tens of millions of miles from the sun. And the Parker probe is going to be 4 million miles. It's going to be closer than anything else we've ever put up there, or natural, except for those comets that maybe struck the sun. And of course, the sun wouldn't even notice, wouldn't do anything. It would shrug the impact off like it was nothing, just like Jupiter did when it was struck by a comet. And Jupiter's far smaller than the sun. So,
how could the sun be struck by anything? Wouldn't it just burn up before it ever touched it?
Well, it depends. But sure. I mean, if it's when it gets closer, it's going to evaporate very, very quickly. But there have certainly been objects that have made it to go into the sun. And if it was moving fast enough, it might not have burned up before it actually went into the photosphere and burned up. But there's another thing, too, to keep in mind. The photosphere is the visual thing that we see, the visual spot. Okay, we see it's the area where the prominences leap off of. We see that in a special light called hydrogen alpha. We see those beautiful arcing prominences coming off of the sun. We see the granulation, the granules in the sun, those little convection cells I was talking about. We see those. We also see in the outer parts during an eclipse, you actually see there's a really interesting outer part to the sun, which has all these wonderful swirls and droops and extensions that stick out from the sun, especially when the moon's blocking them. Then you can see it, and that's called the solar corona. Now, the surface of the sun's about 10,000 degrees, about 5,700 Kelvin, okay, or 5,700 Celsius, sorry. And when the surface of the sun at 10,000 degrees is covered, then you don't have that brightness, and you see the solar corona. Now, the weird thing is, we've discovered that the surface of the sun is only like this 10,000 degrees Fahrenheit, yet the solar corona farther out is over 1 million degrees. Now, that's pretty odd. It's been a long-standing mystery, and thus the Parker Solar Probe's job is to figure out why. And that's what it's trying to do. And it's already made some amazing finds. I don't know, Daryl, do you want to add anything to this at this point?
I think you covered it pretty well, Mark.
All right, I just thought that you might have had something to say.
Well, no, there's still so much we don't know. I mean, what is exciting the corona to millions of degrees? That's why the Parker probe is there. I've heard it speculated in the past that it might be what you might call sound from the sun, so energetic that it's it's heating up the outer atmosphere beyond how high you think it would go. I guess it's still supposition, but that's why we sent the Parker there, was to find out. Yeah,
and there's another thing too. I mean, they've noticed with other probes, they actually noticed something called plasma bombs. What happens is large expulsions of matter off the sun. Now, we know you heard the term coronal mass ejections, but at a smaller scale, there are these little things called plasma bombs. And what happens is they come off the sun, and when they get out into the corona, they explode. And when they explode, they're transferring all of their energy to heat. And that also could be a mechanism by which they're warming up the solar corona. But If you flew through the corona, yes, it would be hot. Okay. However, you might say, well, how could anything reach the sun? The corona would be so hot you'd never get near it. Not true, and that's because the corona doesn't have a density that would be as much as, say, the photosphere of the sun when you get near there. Okay, the logical surface of the sun is at a very dense, different location than the corona. It's what we call a rarefied environment. There's very few particles per square centimeter or cubic centimeter.
It's hot, but it near a vacuum.
Right. So we don't have that. But you know what? We're going to talk more about Parker when we get back. So from Daryl, Amanda, and I, we'll see you on the other side. We'll be right back.
Okay, nurse, let's get this man to the ER stat.
Right away, doctor.
We see this every day. Heart attack or angina pain due to blocked and clogged arteries. Chelation can remove obstructions or blockages from arteries and help avoid painful and expensive surgery. Now there's AngioPrim. It's a liquid oral chelation product that you take with juice. You start to feel the results fast. AngioPrim increases blood flow all over the body, and that means more energy and strength to take on the day with less aches and pains. 60 years of research has gone into chelation, and AngioPrim is the result. A safe and easy way to unblock your veins and arteries from buildup that slow circulation.
Paging Dr. Jones. Please report to the emergency room right away.
Log on now to angioprim.com. That's ANGIOPRIM.com. Or to speak with a trained consultant. Give AngioPrim a call at 954-882-7221. That's 954-882-7221.
Folks, this is very important information. What's to be said about CBD? AncientLifeOil.com. Our CBD is made from hemp and has 0.003 THC, which means this wonderful product won't get you high, no matter what amount you take. What does CBD do for the body? My hands are tied. But you can Google CBD benefits and be astounded. When you're finished reading, you'll want to log on to AncientLifeOil.com. That's AncientLifeOil.com. and purchase. Life is good when you feel good. People are tired of pain. People are asking for non-GMO organic products to help them with, you fill in the blank. Legal in 49 states, and again, our CBD is made from hemp. Ancient Life Oil is about helping people one by one by one. If you wonder how...
vanishing probe. But when we talk about the sun, it's really powering the planets in our solar system. Our planets are doing what they do because of the sun. Yes, they have leftover heat from formation. Yes, they have electric fields generated by their cores. Some of them, not all of them. We'll get there. But the fact of the matter is that without the sun, all of that would be for naught. There'd be no atmospheres that could be supported because they would all freeze out and fall depending on what they're composed of. And so this is something that we have to consider. Now, the sun is made of plasma. What do you mean plasma? Plasma is atoms that have been infused with so much energy that the electrons of the atom are gone. They've completely left the atom behind. That leaves positively charged nucleus, okay? And that's protons, all right? Positive and electrons are negative, all right? So, and from the sun.
I just want to let everybody know watching, we are listening to KGRA Sky Tour Radio with Mark D'Antonio. He's on from 8 to 10 Sunday nights on kgraradio.com. We might just continue it, depending on how long we go. Might continue it into the next show. Not sure yet. We do have permission from KGRA to broadcast almost all the shows. Not all of them, but almost all of them. So, yeah. So you're listening to Mark D'Antonio Show live, Sky Tour Radio, live on KGRA.
There's two bowed ends, like a bow tie that form, a rounded bow tie that form around the north and south poles on top of the paper. If you've never done that, try it. You can buy iron filings from science supply places online. If you look up iron filings, you'll find it. Do this with your kids. It's a fun home experiment. Just don't get the iron near your computer, okay, because it'll short out things, all right? And then take a piece of paper and put a bar magnet on it, or a piece of cardboard, and then sprinkle the iron filings on and watch the shape that comes out. You're seeing nature in action. You're watching the magnetic field, being formed out of this substance, the iron filings, that shows it. Really fascinating. So that said, okay, we have these free protons and electrons that are going around those magnetic field lines. And they rotate pretty quickly, and they're following the sun's turbulent magnetic field. And the magnetic field of the sun has knots and areas where it loops around upon itself. It has things called switchbacks, where, like in a mountain switchback, they go out and they turn around and come back in the same direction they came from, and then turn around and go the other way again. Okay? There's a lot of knots and kinks in the sun's magnetic field. And these free protons and electrons that are streaming out from the sun are following those. Now, this is like, okay, give you an example. It's like a merry-go-round, okay, or a carousel. You're on there, you got the little horse, and you're riding along on a horse. You're going around in a circle. Now you get off the horse, and you walk near the edge, and you're holding onto two poles next to you, and you jump off. Are you going to go in a curve? Are you going to follow the direction that the carousel was moving? Or are you going to just go straight out? That's the question. And the answer is that you just go straight out. So in other words, you're moving in a circular direction, like you're that particle circling around the magnetic field. But once you get free of that magnetic field, you go in a straight line. And so the particles are circling around the magnetic field lines, and when they get far enough away from the magnetic field, they begin to go in a straight line. Here at the Earth, these protons and electrons that we see as the solar wind, they appear to be coming radially out from the sun in a straight, out from the center of the sun or from an area in the sun. Now we know they're coming from what are called coronal holes, okay? Out from these areas of the sun, they come streaming out. We always thought they were coming out radially, like a radius, just going straight out. From the place they're emanated from, they just go straight out. Turns out that's not true. The Parker Solar Probe has found that there's very complicated motions that are being undertaken by this plasma the closer to the sun we get. Now, we had thought that this was a radial motion, and because it is here at Earth. But the probe has made these fascinating discoveries about the solar wind. But let's take a little bit closer look at this. The sun is shedding energy. Everything the sun does gives away some of its mass. And understanding how this works is going to tell us more about how the sun works, of course, but it's also going to give us insight into the future, the evolution of the sun, and perhaps our own fate, when it will die and when. We know that it's too low mass, the sun, to explode as a supernova. But when will it become this red supergiant, or red giant anyway? Our sun may or may not become a supergiant. It might become a red giant. Well, the Parker probe is going to help us study how the sun sheds its mass, because we're studying these particles as the solar flux coming to us. And it's helping us figure out answers to some questions. So, for instance, if we look at stellar evolution, we know that the sun takes hydrogen and makes it into an isotope of helium. That's the main process that creates the energy in the sun. It's a multi-step process, and at every step of the process, energy is liberated. Neutrinos are given off, okay? Well, that said, there's a point where the sun is going to run out of that hydrogen that it uses to make the helium isotopes. Now, at that point, the sun will begin to contract because it's a war against the outward radiation pressure of the sun generating all this energy versus the gravity trying to crush it. All right? But as the hydrogen outward energy, the hydrogen-related outward pressure from the radiative hydrogen to helium process slows down, well, now gravity becomes a bigger quantity and starts to shrink the sun. And what's that do? That pulls some of the hydrogen that's in the outer area around the core that's not fusing, because it only happens inside the core of the sun. It starts to bring some of that hydrogen into the core. And guess what happens? Now the sun says, whoa, hey, I've got more hydrogen. Let's begin fusion again. And it does so in earnest. And when it does, the sun begins to bloat. All right? And through a series of processes like that, the sun will become a red giant. And this is what will swallow Mercury. It'll swallow Venus, and perhaps even the Earth. All right? Now, that process is still several billion years away. Thankfully, don't pack yet. Maybe by the end of this episode, you may have to pack, but I doubt it severely. So the Parker probe has been studying the way the sun is giving off this energy, and the way that it moves, and the way that it interacts with its local environment before it gets here. And this is going to help us figure out the stellar evolution. Now, of course, when the sun is swollen to a red giant, it might be making helium into carbon in its core, because that's the next thing to do in the periodic table, because the suns and stars of the universe are all basically periodic table of the element makers. They are element factories. So carbon might be the end step for our sun, and then once that's over, it's going to collapse into a white dwarf, maybe even making a very pretty planetary nebula around the location that we currently call our solar neighborhood. That said, the Parker probe has been studying how this flux comes off the sun, and it's discovered that the sun produces more particles than we ever thought it did. So in other words, there's more mass leaving the sun than we ever thought there was. And that says things about its age. That says things about its evolution, where it's going to go. And the Parker is orbiting the sun at the same speed that the sun rotates. So it can actually sort of sit over one spot and watch structures developing and dissipating on the sun. And the sun has had a number of anomalies that we could not answer for the longest time. Like the Parker probe has been examining the sun's outer atmosphere, the corona, which I told you about. Now, near Earth, as I said, the solar wind is streaming more or less radially from the sun, but at the sun where the Parker is, the particles are more energetic and they change directions. That's the switchbacks I was telling you about before. They're following weird magnetic field lines that do really strange things. And so the solar magnetic field is full of these charged particles, the protons and the electrons. Protons are charged positively, electrons are charged negatively. And they ride the magnetic field lines near the sun. If you've ever seen a solar prominence in time lapse, because you have to watch them in time lapse, you can't watch them, in real time, because they just hang there. It looks like they're not going anywhere. They're so far away and they're so big that you don't see the movement unless you watch over a period of minutes to hours. If you ever watched one, you'll see that as they dissipate or fall back to the sun, they seem to follow a specific path. Well, that specific path is magnetic field lines that this material, this charged material, is following. So everything is about electricity. And I know Electric Universe people are going to say, yeah, I know. See, that's so, yeah, and that's right. There's stuff we don't know. And I know that that there's some tenets of the Electric Universe theory that are important for solar studies and how planets form and so forth. There is. But I'm not an Electric Universe proponent. I'm just saying that it's a theory that has some truisms built into it. All right. And to that end, I think it's worth maintaining an open mind about and exploring. So when we look at the Parker probe as a probe that's going to shed light on why the sun is doing what it's doing, that's going to really be important. This is the first time we've ever been able to bring something this close to the sun and not have it just burn up. Okay. And the solar magnetic field straightens out by the time it gets here, and we've never known what it does near the sun. Well, now we do, and it's really surprising. Now, here's another thing, okay? It's well known that our solar system has a lot of dust in it, okay? And when we see that dust, we can see it and photograph that dust. And that dust is actually called zodiacal light, or also a part of a particular facet of the zodiacal light is something called the Gegenschein. And these are two examples where we see this backlit dust in our solar system. It's everywhere. I just want to ask Daryl, I've never seen it, but have you ever seen zodiacal light or Gegenschein?
I have seen the zodiacal light many times. I don't think I could honestly say I've ever seen the Gegenschein. The best one I remember seeing the zodiacal light was March of 1997. I was up near the top of Wilkinson Pass here in Colorado, watching and photographing Comet Hale-Bopp when it was at its best, biggest and brightest, and all the sun set, and all of a sudden here was this big, huge, slanting sort of pyramid of white light moving to the upper left from where the sun had set. And that was the zodiacal light, and that's basically all the free dust in the solar system floating around out there reflecting the sun's light.
Yeah.
And it was really spectacular. It looked like a pyramid, but it was sort of tilted over to the left. And it looked really beautiful. And it was a color of sunlight.
That's beautiful. I've never seen a zodiacal light. That's
another thing you'll probably see when you go to Arizona.
I am looking so forward to seeing these things I've never seen before. As people know, when they joined in SkyTour Livestream, there was a point, and that was with an old filter. I'm using a new filter now to look at things, and we're seeing things now we have just never seen before. And Daryl's been there, he knows, and Amanda's been there, she's seen it. We actually have been able to pick up subtle details that have just been really hard to see prior. And I remember looking at something called the Veil Nebula here for the first time, and that was a couple of years ago. And when I looked at the Veil Nebula, I was stunned. I almost cried. I was going crazy because I'd never seen the Veil Nebula in my life, ever, because it was always too faint. But with this new filter and the way I was taking pictures of it with the telescope in the dome, there it was, plain as day, and I was absolutely stupefied. I was like, wow. So you see, this is how, like, when you see new data, like the data coming from the Parker probe, people look at this data and they get all excited, and you might not understand why, but it's like that moment where I saw the Veil Nebula for the first time. The scientists that are studying the way this plasma is streaming away from the sun and coming toward us, when they see these new things, they see this stuff the way it's operating, it's the most exciting thing ever, because they're fully invested in seeing what the sun is doing. And these are the guys that are going to, rewrite the textbook on how the sun's operations are conducted by the sun, if you want to think of it in terms of business. And as we move forward, I know that the Parker probe is going to be it's going to be an amazing set of results beyond what we see already. Now, again, it's only done 3 of 24 passes around the sun, and it's already doing this. Now, when we talked about dust in the solar system, one of the theories was that near the sun, those dust particles that form the zodiacal light, and that's what this is, the zodiacal light and the Gegenschein. I have to define the Gegenschein here for you. But the zodiacal light, that angular kind of column that's coming up from the horizon, that's the backlit dust and leftover debris from the formation of the solar system. So everything when we're looking out into space on a beautiful starry night, you're looking through the dust to some extent that was here. It's basically the solar system pollution that was left over from the formation. And you're looking through that whenever you look out into space at these beautiful objects. Even if you're a Hubble Space Telescope, you're still looking through our solar system's leftover debris.
May I add something there?
Yes.
When you see the zodiacal light, if you can imagine where the sun set, and you trace a line from there right up through the center of that slanted column or pyramid of light, that is the definition of the ecliptic plane. That's the path that the planets more or less orbit around the sun.
That's right.
Exactly. That's the definition of the sun's path across the sky as seen from Earth. But that is the very definition of the plane of the solar system when you look up through the center of the zodiacal plane.
That's right.
And the Gegenschein, by the way, is it's the same thing. It's more dust out in the solar system, but you're seeing it sort of at the anti-solar point up in the sky.
So it's a little brightening. It looks like it's a little brightening, yeah.
Yeah, like a little dim tea bag or something, I guess. It's not nearly as noticeable as the zodiacal light is, but if you're in a really dark location, you can see it. You may see it.
Yeah. Thank you. I was going to define the Gegenschein, but I'm glad you did. Saves me the effort, and you're absolutely right. And here's the thing: this dust is everywhere. But here's the issue. You might think that since it's everywhere, it means it's the sun too, and the answer is yes. However, the theory was that near the sun, those particles of dust are subjected to such high heat that they become gas, and thus the dust should begin to thin out. Now, it's been theorized that there's a dust-free zone, near the sun. I think we have a question in the chat about that. Correct, Amanda?
We did, actually. Ronald had a question about dust before we even got into this. It's like he knew where we were going. So,
smart.
Yeah. He wanted to know, when does the dust burn up? Like, at what distance from the sun?
Yeah, see, that's an excellent question, Ronald. Thank you. The Parker probe is going to confirm this, but the theories suggest that the dust should be fully vaporized by about 3 million miles away from the sun. Now, the Parker probe is only going to go as close as 4 million miles. It's not going to get any closer. However, when it was 7 million miles out, I believe it was 7, it had already noted that the dust had already begun to thin out. So that was telling us that some of this dust had already been vaporized. Maybe there were larger particles. Maybe they had a larger cross-section. And so for that statistical percentage of dust that was a little bit larger, perhaps it was wiped out and vaporized. So about 2 to 3 million miles away from the sun is where that's projected to be no longer an issue. And we're trying to find that dust-free zone. We're looking for that dust-free zone too. Why? Because it's theorized to be there. Now, those of you that know, I do a talk called, it's about where science fails, basically. It's like, what do we do with our science in the face of the unexplained? I've done that talk all over the world, and it's usually very well received. And the reason is because people want to know whether science has all the answers or not. And I sit there as a science guy and say, actually, no, it does not. We don't have all the answers from science. And this is another example, where we have some things that science predicts and we see are working, and we can say, yes, science predicts, and we can test and show that these things are true. That's all good stuff. All right. What we don't know, however, is how some of the mechanisms actually work. One thing is the sun's corona is over 1 million degrees, sometimes as high as 3 million degrees, and the surface of the sun's only 10,000 degrees. What makes the corona hotter? Well, possibly the Parker probe is going to find out and tell us. It could be because of all these very tortuous paths following the magnetic field that these particles are taking closer to the sun, which will be in the corona. Okay, they'll be moving around before they leave, and as they get out of the corona, perhaps they're straightening out in their path, and maybe they actually define the actual shape of the corona, and that's something we're going to find out. Again, the Parker probe's only done 3 of 24 orbits, so I think that we're talking about something that's going to be quite an eye opener. All right, but that said, since the Parker has seen this tapering density, it shows that science has correctly predicted that. Just like science correctly predicted the actual visual that we would get from the black hole that we photographed for the first time in Virgo in Messier 87, a gigantic elliptical galaxy, based on the projected and prevailing theory, the shape of this black hole should have looked a certain way, and theoretical calculations showed a particular shape. The actual visual of the black hole showed exactly that shape. So that's, for instance, a place where science doesn't fall down. Science does work. And we only know 2% of our universe. Now, some of you who know me know I've said 4%. Well, ostensibly we know 4% because 73% is dark energy, 23% is dark matter. And I can explain in another show what those two values mean and why they come about, and what failings of science bring them about. But that means that there's only 4% of the universe we understand, and of that, only 2% that we can find. The other 2% is missing mass, and that's a whole nother problem. So with what we know, science sometimes doesn't give us the right results. But the Parker probe, the predictions are coming true. The predictions for the science, the predictions for what we're going to see are actually, they're correct. Now, the results are still surprising because we're seeing new things that we didn't know to even think about predicting, like the fact that the solar wind is moving in a straight line where we are, but not at the sun. That we didn't know. We haven't been this close to the sun. We've never done this. But by September of 2020, that's going to be another time where when the probe is at 4 million miles from the sun, that's going to be a time where we're going to see, probe willing, some new data that we may not ever see again. But boy, the Parker Solar Probe, a shining star among the stars. Now, I just want to say we have less than a minute left, but I want to ask Daryl or Amanda if you've got anything you'd like to add before we close out the Parker Solar Probe concept.
A question actually came in about the Parker satellite or probe.
Okay. We'll have the break.
Pardon?
We can talk about that after the break too. Yeah.
Sure.
I'm good.
All right. So, folks, stick around. And if you have any questions, you can call our dial-up line. We're going to open the lines. And if you want, it's KG. It's 1-800. Is it 800 KGRA Live? Or is it
855-472 5483.
Right. Okay. So it's is it 855 KGRA Live? Oh no, it's
KGRA Live.
KGRA Live. I'm sorry, guys. I got it now. Okay. Yes. And if you want to calculate, I hate the letters because that's like, it's clever, but it makes you think. And you don't want to think when you're trying to get to the phone quick. 855-472-5483. We will talk to you in just a minute.
whole lot easier.
The only place you have to go to hear all about the greatest science on planet Earth. And my name is Mark D'Antonio, and I have with me Amanda Curran, my wonderful co-host, and Daryl, my other wonderful co-host. Between the three of us, we should be able to handle all things astronomical. And just ask Amanda, because she didn't know any astronomy in the very beginning. And now Amanda is literally a whiz at astronomy. She's got.
I wouldn't go that far, but
Amanda created a show, a game about astronomy on a stream last night.
That's right.
It was lots of fun.
That's right.
Yeah.
That's right. And I want to give you some kudos on that. In astronomy, we have these objects in the sky, and sometimes they have some very colorful names, like the Witch Head Nebula and things like that. Witch's Broom, okay? And well beyond that, there's the Lonely Hearts Cluster, there's the Broken Heart Cluster, there's
a Christmas Tree Nebula.
There's a Christmas Tree Nebula, that's right. There's
Cluster, sorry.
That's Christmas Tree Cluster and the Cave Nebula, which is part of that complex. And of course, so what Amanda decided to do on her own, okay, being the astronomical star that she is, she said, hey, some of these names are kind of clever. Let's see if I can give clues and then have people guess what the object is. So, for instance, she said, this is a cluster where people that are sad or haven't found love go, something like that. And, of course, she's talking about the Lonely Heart cluster. Or, these are people that lost a loved one, I mean, that's sort of those are bad examples. She also said something like, for one of these others, this is first in its class, but a tasty meal. Now, it really have to think about that. And when she means by that, and those of you in the chat, some of you might get it and some of you might not, and some of you listening might. Well, what she meant by that was first in its class, meaning first in the list. And that's Messier 1. Charles Messier put together a catalog, and Messier 1 was this object, and a tasty meal. Its name is called the Crab Nebula. M1, the Crab Nebula, and that's the answer. So, you see, that's how the game is played. It's intellectual. You have to think about it, and our own Amanda came up with it. I'm so proud of her.
Oh, thank you. I appreciate it.
It's great. It was really, really cool.
I just I enjoy our community that comes out, our listeners, and just wanted to engage them and, have some fun while we were learning. And, on Saturday night, looking at the stars, why not have a laugh amongst friends?
And it was a really fun stream.
Oh, thanks. I enjoyed it.
Yeah, and the funny thing is that as soon as I closed up, it clouded up. So as soon as I decided to end, it clouded up. It was great. It was perfect timing. This clouds finally listened to me for once. It might have been that nuclear weapon I set off up north, though, and I obliterated Vermont. But, hey, I got clear skies for a little while. Little joke there. Anyway.
Care to elaborate on that?
No, it's a joke.
Okay.
Yes.
Very little joke.
Very joke, apparently. Let's forget it. Let's rewind here. Okay, went backwards, and now we're going forward again. I have a caller on the line, and I think we would like to say hi to this caller and take their question. Are you guys up for a question or two here?
Let's go for it.
All right.
Only if it's from Ronald.
Oh, well, then I don't know.
This isn't Donald, is it? I bet it's Ronald.
You think? Want to take some bets?
No, I won't take that bet.
Okay. Well, you should have, because you'd have won. Hello, caller. You're on the air. Please state your name and your business here. This is Mark.
Hello, this is Ronald from Minnesota.
Hey, Ronald.
Hi, Ronald.
We didn't have
Hello, Ronald.
hello to Daryl and Amanda, and we didn't have snow today, but we had fog like crazy. Couldn't see.
Must have been warm.
But okay, I had a couple of questions with the Parker probe.
Sure.
I call it a satellite, but it is a satellite essentially. But probe because it's looking into the sun. I got it.
Yep.
I was reading the article about that, and they talk about as it goes by Venus, and this was my question that Amanda was going to ask. I figured I'd go ahead and ask it. What is the effect that Venus's orbit would have on the probe, and how much would it affect its swing around the sun? And then another question about
Sounds like Daryl wants to
the
answer
light.
that.
Well, are you
Yeah,
talking
you
about a
can-
gravitational assist? It was when the Parker was on the way to the sun, it passed Venus.
Oh, is that what it did?
Is that what you meant?
I don't know if that's what it did. I don't know if that's what they were talking about, or if they were talking about Venus affected the orbit.
Scrub that speed off before you can start approaching the sun. And in other words, you have to gain a lot of velocity relative to the sun, and they do that by flying by Venus and or Mercury in order to change its direction and its speed.
All right, thank you. Good answer. And
It is a
it's
good
amazing
answer.
how
Very
we
good,
can
Ron.
figure all that.
Very good.
Good.
I mean, sorry,
Good
good,
way
Ronald.
how we can figure out all that math on that, you know. And then the other question I had was about the light. I remember when I was on my ship back a long time ago, and I was on the Indian Ocean, though, and I saw what they used to talk about, the green flash at sunset. You know about that?
Yes, of course.
Sure.
And then I don't know if that's part of the Zodiacal light that you were talking about.
No, that's the Earth's atmosphere refracting the very last rays of the sun before it sets.
Yeah.
It's sort of like a prism effect, you know, where you'll see a green flash right at the very top edge of the sun in the very last moment before it sets below the horizon.
Yep.
Yeah, you have to time it exactly right. So, anyway,
Well,
thank you for your
if you run
show,
a high
Mark.
resolution
Great
video
show.
camera with a neutral density filter on it, you'll actually probably catch the green flash, and you can always rewind it and go back to that spot and
there you
extract
go.
a photograph of it. Because some of these
a good
video
idea.
cameras now, they're 4K, a very high resolution, so effectively you'll get a 4K photograph.
All right.
Which is,
and, happy holidays to everyone. All right.
Thank you. Same to you,
I'm
Ronald.
not going to say Merry Christmas yet.
You as well.
I'm not going to say Merry Christmas, but I'll say Happy Holidays.
Well, you know, I guess
right,
to
I'll
be
say
politically correct,
Merry
we have to
Christmas
say
when
Happy
it's closer.
Holidays.
Merry Christmas.
All right. Thank you, Mark. Thank you, Amanda. And thank you, Daryl. And thank you, Bill. And everybody
You're
have a great
welcome.
day.
All right.
Bye.
You know, could I touch on his first question just a little bit more? We have gotten so good at that. It's like being the solar system ace snooker player.
That's
you
right.
know, that we can calculate and aim at and hit such precise spots moving by other planets that we can make what we, you know, that cue ball, we can make it go wherever we want to and do things with it that we can't do by ourselves from Earth.
Yeah. Here's something to keep in mind too, Daryl. And for all you listening, this is true too. When we're aiming at, say, let's just say Mars, getting to Mars is not easy, okay? But we send the probe in the direction where Mars will be when we get there. So we're sending it in a direction that's not even where Mars is. But by the time the probe gets there, Mars will have swung into that position. Yep. See, so imagine being the guy or the woman, the woman or man that has to calculate that. Well, it's actually neither. There's actually advanced programs written by teams of people that can calculate exactly what you have to do, how long the burns have to be on your probe, when you have to shift directions, when you have to apply burns, for how long they have to burn in order to get the probe on that particular course. And it all starts with a launch that has to be perfect, absolutely perfect. Because if you're off at the beginning, you're vastly off by the time you get to your destination. So you have to be so close to proper that you only need a small amount of fuel to make some kind of course correction. And usually those course corrections are made on the cruise stage when the thing's on its way out there, and it's going to be cruising for, say, like 10 months, you know, straight. Then you can actually make small corrections, and it'll have a huge effect on your final destination.
Yep.
You know, just imagine you have a very, very long stick that's a mile long. Well, if you just move it a half an inch where you are, it's moved quite a large distance at the other end, you know, as you're picking it up into the air. And that's how this works, you know. So and as Daryl says, we've gotten really, really good at it. I mean, so good it's impossibly accurate, you know. You know. So I wanted to talk about something tonight that it kind of relates to the Parker Solar Probe, and that's magnetic fields. You know, I know that we've talked about magnetic fields before, and I think that it sort of behooves us to kind of go through what is a magnetic field, because the magnetic field is the reason we exist. We're alive because of that magnetic field. I think you would agree with that, Daryl. You know, and I think that.
Sorry, yeah, I agree. Sure, it's one of the four universal forces.
Yeah, yeah, and so when we talk about what a magnetic field is, we have to actually talk about how they're generated, and we're going to talk about that too as we go on here. But you know, when we talk about the energy and intensity of the radiation that hits the atmospheres and streams into a planet's magnetic field, you know, the solar wind that we've been talking about, the Parker probe is detecting, as it gets to the Earth, that solar wind is more uniform, moving in a straight direction pretty much. And it strikes our magnetic field. And those charged particles do the same thing at our magnetic field that they did around the sun. They kind of circle around the magnetic field lines, and they get trapped. And they can stay there for a long, long time. And these trapped particles have become what's known as the Van Allen radiation belts. And we say radiation, but you know what? It's really not radiation per se, in terms of the ionizing radiation, in terms of, say, electromagnetic type radiation. It's really not the same. It's a different variation. So it's just nomenclature that's stuck over time, calling it radiation belts. So when people say, well, we can't go through the radiation belts, you know, the astronauts will die, so we didn't go to the moon. No. We go through the radiation belts so fast that the astronauts didn't even notice, okay? But we do have to concern ourselves with it, especially at times of high solar maximums when solar radiation is generating lots of flux, which causes lots of radiation or a lot of trapped particles in our magnetic field. Okay, so the thing is, if we talk about the magnetic field, okay, magnetic fields are generated by electrical currents. All right, now how do you know that? Well, you know that because when you were in grammar school, you created a simple electromagnet. You took a coil of wire and wrapped it around a nail, and you put a battery on the both ends of that wire, and then when you touch the nail to something like a paper clip, it stuck because it was now an electromagnet because of this battery. All right, so an electrical current generated a magnetic field, and it has to do with the coiled wire. Well, in the same way, we can imagine on a much larger scale that we can get magnetic fields around planets. How's that happen? Well, when we look at how a magnetic field actually occurs, all right, we have to go and look at the theory. And I'm not going to drown you in science, technology, and mumbo jumbo, but we're going to talk about it in just plain terms. It's called the dynamo theory, about why Earth has a magnetic field, all right? And when we look at our magnetic field, we consider the source. So it's the dynamo theory is the mechanism by which a planet can generate its magnetic field. And how would we recognize this dynamo effect taking place in our real world when we look around every day? Well, have you ever seen a bicycle that has a light on it that's powered by the cycle of the pedals? When you pedal harder, you get a brighter light. Have you ever seen those? All right, it's a little tiny. Yeah, it's called a dynamo. It's this little thing you attach to your bike, and there's a little wheel on it that spins along on the rim. All right, and as you pedal, that little wheel spins, and inside this housing are little magnets. These magnets spin, and there's a wire coil inside there that is now getting with the magnetic field shifting, all right, and changing. It actually imparts an electric current to these wires, which go to the light and turn on your light. Okay, so that's how a dynamo works. All right, as you pedal the wheel, touching the rim of the bike, the small magnets rotate, generate an electrical current on the copper windings inside that housing. Well, guess what? It works the opposite way. All right, and on planetary scales and stellar scales. Electrical currents can generate a magnetic field in reverse, all right? So the magnetic field generates electricity for your bike light, but electricity also generates a magnetic field. It goes the other way too, all right? So at planet scales, the magnetic field can be large, as well as with stars. And the way it works with the Earth is actually the following. The Earth has an inner core, and it's solid iron and nickel, all right? It's about 2/3 the size of the moon, and guess what? It's as hot as the surface of the sun. It's 5,700 degrees Celsius, or 10,300 roughly Fahrenheit, all right? And at that temperature, you might say, "Wow, that's pretty hot. How come we don't burn up?" Well, it's because of the fact that there's overlying material and lots of mass between us and that. Okay, outside of that solid core is the outer core, and that's actually liquid, because the pressure is less, and the liquid iron there can actually flow more like a liquid. And it's about 1,242 miles or 2,000 kilometers in diameter, all right? And that iron and nickel material, because of temperature differences between the inner core and the outside of this outer core, it causes convection cells to form. And so hot material rises away from the inner core and then cools and goes back toward the inner core and then comes back up again. Meanwhile, as the Earth rotates, there are swirling eddies and little whirlpools of molten iron and nickel that are caused, and that's from the Coriolis force. This process of this material moving against the inner core like that is creating an electric current. So basically, the dynamo theory is that electric conducting fluid, like this inner conductive fluid, these iron, under rotation will generate a magnetic field. It's experimentally provable. It's part of electrical engineering. We've done that. We've created this. We've used this process to actually create new technologies here on this planet. So it's all observable in nature as well. So in a practical sense, this liquid iron in the outer core is moving around, and as it does so, the electrons in that conductive fluid create the electric current through their motion. And the energy of this moving fluid is converted into a magnetic field. And this magnetic field is what protects us by shunting those high energy particles from the sun away from us as they strike our what we call the magnetosphere. The magnetic sphere, basically. I say sphere, it's not a sphere at all, that protects us. So let's just talk about what our magnetosphere looks like. Now, what is that? Well, the magnetosphere is the region of influence of the magnetic field around our planet. So as a solar wind comes toward the Earth, it first encounters the outer area of our magnetic field. Okay, there at that point is created something called a bow shock, B-O-W, a bow shock. Right? We've seen the bow shock. In other planets. I remember when the Voyagers first saw the bow shock of Jupiter, and they could actually hear it. It was a static, but it was really cool. When the solar wind hits the outer area of the magnetic field nearest the sun, we get this bow shock, and it begins to cause our magnetic field to drape behind the Earth a little bit, and that becomes what's called a magnetotail, kind of like a comet's tail. Always pointing away from the sun as the Earth goes around. However, it's one of these things that's the magnetotail is something that is a sort of a protective tail behind the Earth. Now it's huge compared to the Earth. All right, and this is the theory about how we can terraform Mars by creating a highly charged magnetic field between Mars and the sun, maybe a few 100,000 miles away from Mars, at a Lagrange point, say, a point like a parking spot in space between between Mars and the sun. And if it generated a magnetic field, the solar particles would strike it and drape it around Mars and protect Mars. And then Mars, with its normal processes, could actually start to, terraform itself, because Mars generates its own oxygen a little bit. Mars generates its own other chemistry, and Mars generates some water. It's just that it gets destroyed by the ultraviolet radiation striking the planet. And speaking of all these planets, here's a question. What planets in our solar system have a magnetic field? And I'll pose that question to, let's see, Daryl, Amanda. Okay, Amanda.
All of them.
Okay, very good. That's a safe, attempt at an answer. And the answer is, to some degree, all of them. That's true, but not.
Maybe not Mercury or Venus.
Well, Venus doesn't have a magnetic field for the same reasons that we do, but Mercury does. Mercury is one of the actually Earth and Mercury are the only ones that have a magnetic field that's created by liquid metal at the core, which is what we do. Okay, and that will last billions of years. Okay, so Venus, though, it doesn't have a magnetic field per se. However, the upper ionosphere of Venus, Venus rotates very slowly. The upper ionosphere of Venus, is still protected from the solar wind because it's using a different type of magnetism. All right, the ionosphere interacts with the solar wind particles, and it sort of acts like a magnetic version of that comet tail we talked about earlier, like a magnetotail. So it's kind of like a long, skinny-looking tail that doesn't look anything like ours. But it does have some protection. Now, we go to Mars. Mars doesn't have a conventional magnetic field. We know that for a fact. But there are areas that are called crustal magnetic localizations, kind of a thing. There are some crustal magnetic fields on Mars. And they kind of form a little dome around that certain spot. and help protect Mars in that area. Maybe we'd put a habitat there, for instance, for the first time when we finally got there. But we'll talk about Mars' magnetic field on a future show a little more. Jupiter has a magnetic field 20 times the size of ours. It's really powerful, really strong. But it doesn't actually, its magnetic field is created by the core of Jupiter, but not through liquid metal. It's actually caused by liquid hydrogen, but it's called liquid metallic hydrogen because under pressure, a hydrogen can take on the properties of a conductive fluid. Similar, Saturn is like that, okay?
And we see aurora over the poles of both planets, I believe.
That's correct. We do. We see auroras over Jupiter's poles and Saturn's poles. And Uranus and Neptune are also true magnetic. However, the funny thing is Uranus's magnetic field is off by 59 degrees, okay, because Uranus is flipped on its side. Neptune is fine. Neptune has a magnetic field, but it's also slightly tilted away from its axis of rotation as well. So magnetic fields are intrinsic to planets for part of their history. Anyway, I'm sorry to tell you that we are out of time for this night, and we're going to have to go. But I want to thank you guys for joining us, and I hope that you will come back and see us next time. And if you haven't already, please go check out SkyTour Livestream on YouTube and hit that subscribe and go ahead and click the bell so you get notified when we take the observatory live on those clear nights. All right? So I've enjoyed talking with you guys. Thank you, Daryl. Thank you, Amanda.
Thank you, Mark.
Thank you, Bill.
you